Hello friends, welcome to my channel once again, and today we are going to learn about the Bragg's condition or Bragg's law. Okay, so this law or this condition is necessary for X-ray diffraction. So in the last video we have seen about the XRD, or we know that what is this XRD now. So XRD stands for X-ray diffraction. So in the last video we have seen about this X-ray diffraction, and we know that the X-rays are getting diffracted from the atoms, moreover from the electrons, but we call the from atoms, and these atoms are equally spaced in a crystal. And here a condition is that what for the diffraction, the atomic spacing must be comparable with the wavelength, and then we can have the diffraction. And yes, we know that the X-rays are having very small wavelength, a very short wavelength, a narrow wavelength, and due to that narrow wavelength it have the more energy, right? Or energy will be maximum. If we have the large frequency, then we have large energy, but wavelength is small means frequency is very large, and frequency is large or frequency is greater means energy is greater, and therefore we can say for the shorter wavelength we have large energy. And now that energetic X-rays which are having very short wavelength, which is nearly comparable with the atomic spacing, and therefore we can have the diffraction, and we call it as X-ray diffraction. In the last video we have seen up to this. Okay, now for this X-ray diffraction, Bragg have seen, or Bragg have done some experiments, and he got some diffraction results, and he found that there is a condition when the X-rays are following this condition, then the X-ray diffraction is possible. The X-ray diffraction is possible, and that condition we call it as Bragg's condition or Bragg's law. Okay, Bragg's condition or Bragg's law. Now in this video we have to see this only. Okay, right. So let us begin here the Bragg's diffraction. So I think this part we have seen, but here again we will see what exactly the Bragg's diffraction is this. So in the crystal, or here what the Bragg these two Bragg scientists, William Lawrence Bragg and William Henry Bragg, actually they are father and son. So they found in 1913 what the wavelength, if we have for a certain crystalline solids, right, for a certain specific wavelength, and incident angles, because incident angles means this particular X-ray. Now this X-ray is having, or this X-ray beam is incidenting on this particular crystal. Let us consider the angle of incidence. Now if we talk about this is the normal, then this will be the angle of incidence. So with a specific angle of incidence, right, this is angle of incidence, this angle we know it is called as glancing angle. Okay, and the intense peaks of the reflected radiation. Now what they found, there are intense peaks of the reflected radiations, means after the reflection. Now this is what the reflected beam. Okay, we can call it as reflected X-ray beam. Okay, and what is this? This is what the incident beam. So what Bragg found in 1913, they found an intense peak. Here is what the intense peak of reflected radiation, and that why it is happening, and from that intense peak what they have derived, that is what we have all the Bragg's condition. Okay, so right now just what we have to consider, here we have a simple material, let us consider, and on that material we expose that material with the X-ray which is incident, and now it gets reflected beam, but at a particular angle of incidence, and a particular wavelength of the X-ray, what we got, this reflected peak, we got very intense reflected beam, and from that we can say yes, there is atom present, and where we got this not intense, a very dark point, then we can say the atom is absent there, and from that we can derive the materials interplanar spacing, or we can derive the interatomic distance, or we can have the structure. We know that XRD will give you the direct structure like this. Here is atom present, here is atom, we can say. So this particular thing we can bring, but what first Bragg's condition we will see. So that exactly happens in Bragg's diffraction. Okay, now Bragg diffraction occurs when electromagnetic, whatever we said, that is what electromagnetic radiations of subatomic particle or subatomic particle waves, electromagnetic radiations or subatomic particle waves with a wavelength comparable to the atomic spacing. This condition already we know. To have the diffraction to occur, we must know the wavelength must be comparable with that particular object size. Now here who is the object? Atoms are the object, and their spacing is nearly comparable with our wavelength of the X-ray, and therefore we can say yes, diffraction is possible. Are incident upon a crystalline sample scattered by the atoms in a system and undergo the constructive interference. So why we are getting an intense peak? Here is a constructive interference, and that is accordance with our Bragg's law. Okay. Now since wavelength of some X-rays are about equal to the distance between planes, again we have the interplanar distance. That means what? Here I have considered initially only one plane. Here we have some atoms, but it is not possible. We are having a crystal with multiple planes. Now this is the second plane, okay, and we can consider one more plane. This is the third plane, and here we have this periodic arrangement of atom, and this distance between any two successive plane we call it as interplanar distance. So it is denoted by D. Atoms reinforce diffraction peaks of radiation varying intensities and can be produced when a beam of X-ray strikes on a crystalline solid. That's what we are saying. When we strike this particular material with a X-ray beam and we are getting some reflected beams, right? Let us consider these are the two rays we are considering, and the reflected these two rays. This is 1, 2 incident. Now this is 1, 2 reflected. Now these two reflected rays are getting reinforced. Using constructive interference, and that's why we are getting here. We know that whenever there is a constructive interference, we have bright point, or we can say yes, bright band, but here we are having peaks, and therefore we can say we have a intense peak. So this intense peak is only because of the constructive interference. So that is what exactly happening for the scattered beam. Okay, constructive interference, or the scattered for the scattered or reflected X-ray beams, they are interfering with each other constructively, and therefore we are getting a intense peak, and that peak is nothing but in accordance with our Bragg's law. Okay, right. Now next we will see exactly what is Bragg condition. So this is what exactly happened in Bragg's diffraction, how the diffraction takes place. Now we will talk about this Bragg's condition, or it is also known as Bragg's law. Okay. Now for that, let us consider a monochromatic single wavelength beam of X-ray to be incident on a crystal. We know that we are interested in monochromatic beam, and the horizontal lines represents the set of parallel planes with Miller indices HKL. Now this Miller indices is some different concept, but we can say it is a notation, or we can say it is specification for the planes. Okay. Now in this diagram we have considered these two planes with the interplanar spacing D, small d. Okay. So this is what interplanar distance means, distance between any two successive planes. Okay. Now you can see in the diagram only, this is what the incident X-ray beam, and here it is outgoing. That means we can say the reflected X-ray beam, and yes, this X-ray beam, and we have here a detector which is detecting that particular beam which is getting reflected from the atom. Now this first ray, see here, it is getting reflected from first plane, second ray is getting reflected or getting scattered from the second plane. Okay, this theta is, we have considered here, that theta is nothing but the glancing angle. It is not incident angle, remember, that is the glancing angle, because angle is made with the interface. So that angle we call it as glancing angle. This is not the angle made with the normal. If we call this as the normal, okay, and if this is the incident ray, right, we know that we name it as IR, that means incident ray, and if this is the reflected ray, now this angle made by incident ray with the normal, we call it as angle of incidence, but this angle, it is theta g, or we call it as glancing angle. So that angle is glancing angle. Okay, right. Now let us consider theta is a glancing angle, and with that glancing angle, and after the reflection also we are getting here, that is what the glancing angle. Okay. So here we have considered two planes, and those two planes are exposed with the X-ray beam. These are the incident X-rays, and then yes, next what we will see, after the reflected, they are detected by this detector, and if they are having in the same phase, if the reflected must be in the same phase, if these reflected reflections must be in phase to detect the signal, because if they are in same phase, we will have the constructive interference and we will have the bright band, and then we can have the detection of that particular rays in our detector. Otherwise, we will have the black spot, that means there is no atom present, right. Now, yes, that diagram we have explained here. When an atom or when an incident beam of a monochromatic X-rays of wavelength lambda strikes this set of the planes at an angle such that the wave patterns of the beam leaving the variation planes are not in phase. That means if they are not in phase, then there is no reinforcement and beam will be no any spot we can have here. Moreover, here it is destructive interference. Destructive interference, if both the rays which are coming out, those are not in phase. But on the other hand, if these reflected beams are in phase, if both the beams are in phase, then reinforcement means yes, there is an increment in the amplitude and of the beam, and then we are having the constructive interference. So this is what important for our purpose. This destructive interference will give you the dark spot, that means the space between two atoms we can say here, right. But here this will give you the peak, that is our intense peak, and that will represent actually the position of atom. Okay, right. Now, yes, now consider the beam. Again we are considering the same beam. Here mathematically we have to derive one equation, and that equation is nothing but Bragg's condition or Bragg's law. Okay, now consider a incident X-ray. Let us consider, we name it as 1 and 2, and yes, here it is 1 and here it is, this is 1, this is 2. These X-rays are falling. Now for our understanding purpose, I will draw here one more diagram for the bigger side. Okay, let us consider these three are the planes, and yes, obviously we have the interplanar spacing D, and I will draw a normal with a dotted line so that we can understand exactly where the rays are getting incident and then reflected. So this is happening with respect to first ray, and this happens with respect to second ray. First and second, obviously these are the X-rays, more or monochromatic X-rays which are having same wavelength, single wavelength. And then after reflection, yes, here it is going and here it is going. These are the reflected, so we call it as 1' and 2', and here we have our detector. Okay, here it is detector, right. Now, so what I am saying, this angle is theta, that is the glancing angle. Okay, now in the diagram we will consider, we will just draw one perpendicular from this side, okay, and one perpendicular from this side likewise. Okay, so this is a perpendicular, that means it makes an angle 90 degree. Okay, now let us name it as M, this point as M, and this point as N, and this point as P. Okay, right, and this origin point we can call it as O, right. So since that angle is theta, okay, so this angle is also theta, right. You can say this is theta, therefore this will be theta, and therefore this will be again theta, this will be again theta. Okay, so this angle MOP is theta, and angle NOP, it is also theta, and we know that is what the angle, glancing angle. And if we talk exactly about this particular ray, whether this first ray or second ray, if I am talking about the first ray, then see here, this is what the original path of first ray, but now the new path will be this. So the total angle, we can say the diffracted angle, this much will be the diffracted angle. Among that, this will be the half theta, and this is also theta. So that means actually this angle will be 2 theta. Now if you got the point, why we have in the X-ray diffraction, we have the graph between 2 theta and intensity. So actually the 2 theta is nothing but the angle of diffraction. So whatever may be the X-rays falling on that particular crystal, they are getting diffracted. You can say similarly for this second X-ray also, those X-rays are getting diffracted by the angle 2 theta. Okay, right. Now we will have to derive some mathematical portion. So for these rays to be in phase, now if we want these 1' and 2' must be in phase, then we have to see whether they are traveling the same distance or not. Now you can see carefully, I will change the pen. Now this is what the first point at which the first ray is incidenting. This is what the point where the second ray is getting incident, right? Now see, this up to this point both the rays are traveling equally up to point M, and after the point N again both the rays are traveling the same distance. Yes, yes or no? From this you can say yes. I will draw this one like this. So this will be the extra distance, this and this. That means MP plus Pn. This will be the extra distance traveled by which ray? Second ray. Extra distance traveled by second ray. Traveled by 2 or ray 2, because we know that up to this, up to OM, yes, up to this plane you can see, up to this plane both the rays are traveling same distance, and after this plane ON both the rays are traveling same distance, but this much means MP and again Pn or NP, that is what the extra distance traveled by our second ray. Now, and what we call this extra distance as? This is nothing but the path difference. Yes or no? We know that we have two different rays, and if one ray is traveling little bit larger or less distance, then that is what we call the path difference. Now this path difference only decides whether they are getting interfere constructively or destructively, or they are in phase or not. And now if we want they must be in the same phase, then this path difference must be integral multiple of lambda, that means n lambda. Then and then we can say we have constructive interference. Yes or no? Constructive interference. This is the condition required for constructive interference. So what is the condition? Path difference must be integral multiple of lambda, or we can say half multiple of or even multiple of lambda by 2. Even multiple of lambda by 2. 2n is even number and divided by 2. That means 2 will get cancelled and it is again n lambda. In 12th standard you have seen like this. This will be the condition for the interference, constructive interference. The path difference must be even multiple of lambda by 2. 2 get cancelled, and what we got? N lambda. So in other hand we can say it is n is what? Integral number which starts from 1, 2, 3 and so on. So n is the integral number. That's why we can say directly the path difference must be integral multiple of wavelength. Then and then these two rays will get interfere at the detector constructively. Yes, right. Now we got this condition, path difference must be n lambda. Now yes, this is what path difference, but we can find the path difference, what is exact path difference, from the diagram. Okay, now just we'll move towards this last slide. Okay, I will draw the diagram one more time. So because now I will just draw, sorry, two planes. Okay, this one and the first one. So this is first and second plane they are separated by the distance d, and again if you remember, this is what the normal we have drawn, and yes, this is the first ray. Okay, and yes, this is the second ray. They are getting reflected from this, and this is again we name it as 1 prime 2 prime. Okay, and again we have drawn, these are the two perpendiculars. It is M, it is N, it is O, and it is P, and we know this angle is theta and this angle is also theta. Now what is our target? We want to find the path difference, that is Mn or Mp plus Pn. This is what we got up to this. It is path difference, and that path difference must be equal to integral multiple of lambda. Then and then we have constructive interference, we know. Now our target is to find what is Mp plus Pn. So now in this particular, because this is what the 90-degree angle and this is also 90-degree angle. Now just talk about in triangle, I will write here, in triangle MOP, in triangle MOP, or we can say in triangle PON. You can take any one of the triangle because both are exactly same. So in triangle MOP, it is a right angle triangle. Now this is what the 90-degree angle, and the side which is in front of 90 degree, that will be the hypotenuse. Now this will be the hypotenuse. OP is hypotenuse, and that is what? D. OP is D. So let us use the definition of sine theta. So sine of theta with respect to this theta, what is sin theta? Opposite side. This MP is opposite side. Opposite side divided by hypotenuse. What is hypotenuse? Now this is 90-degree angle. That's why the side which is in front of 90-degree, that is OP. OP is the hypotenuse. Similarly, in triangle, second triangle, you can see what is that second triangle? PON will have again same definition, sin theta is equal to, now with respect to this theta, this will be the opposite side, that is PN divided by what is hypotenuse. Again with respect to this triangle also, OP is the hypotenuse, right? Okay, now what is MP? What is MP? If you see, MP is what? Our side for which we have to derive. So MP, can I write this OP to that side? So it will be OP into sin theta. Again we have to derive the PN. So PN is equal to, what is that? OP into sin theta, right? Yes. Now see here, what is OP? OP is nothing but our hypotenuse, and which is nothing but interplanar distance. So I will write D sin theta. Similarly in this equation also, D sin theta. OP is nothing but D. Now we want this equation. So if I am writing that equation, this side first of all, path difference, it is n lambda. So n lambda and MP. Now what we have calculated, this D sin theta, MP. Pn is also D sin theta. So D sin theta plus D sin theta, and it will be 2D sin theta, and to the left hand side we have this n lambda. So actually this is the Bragg's condition or Bragg's law. Okay, so whatever we got here, n lambda is equal to 2D sin theta. This is known as Bragg's law. Bragg's law or Bragg's condition. So what is there? N is nothing but order of the spectrum. Order of the spectrum, that means order of the diffraction pattern. We can say lambda, we know that it is wavelength of the incident beam, X-ray beam, right? Then what is D? D is nothing but the interplanar distance. Interplanar distance. And what is theta? Theta is nothing but the angle of diffraction, we can say, because actually the 2 theta is angle of diffraction, but here we can say theta is an angle of diffraction, or we can say the glancing angle. Okay, so this is how, if we know this condition, n lambda is equal to 2D sin theta, then we can say yes, that particular X-rays which can satisfy this condition can occur the Bragg's condition or Bragg's diffraction. Okay, right? So in generally what happens, generally we talk about the first order diffraction only, and therefore we can say n is equal to 1. For first order diffraction, n is equal to 1, and therefore n is 1 and this n becomes 1, therefore lambda is equal to 2D sin theta. Now D suffix HKL, you can have this HKL nothing but HKL are nothing but Miller indices, that is the specification of plane only. Okay, right. So this is all about Bragg's law or Bragg's condition. If you have any doubt, you can post in the comment box, or if you feel this video is a value addition to your knowledge, then you can like this video. And for more such videos, please subscribe to my channel and go to the playlist and watch all the previous videos also. And lastly, press the notification icon so that you will get the notifications of my next videos, right? So guys, this is all about the Bragg's law, and thank you so much for watching this video. We'll meet in the next video very soon. Till then, take care and keep learning. Thank you very much.